In this video, we are going to introduce complex numbers. So, if we consider the equation x squared equals a number, whenever that number is a positive real number, then we always get two solutions. We take the square root of both sides and we get plus or minus the square root of a. However, we notice that if a is a negative number, a negative real number, then I can't do the square root anymore and get a real number, right? We don't have anything that squares to a negative number if we require the number, the x here, to be real. So to deal with the situation, we introduce what's referred to as the imaginary unit, or we just typically simply call it I, and we define I to be the square root of -1, so that when we square I, we get -1. So that I is now a solution to the equation x squared equals -1. So, to show you how we can use this in simplifying some radicals, let's say we wanted to simplify the square root of -49. Well, -49 we can think of as -1 times 49. The square root of the -1 will be I, so that will be I times the square root of 49. And then we can simplify square root of 49 like we always have and write it as 7. So we get an answer of 7i. Likewise, we can do, say, square root of -75. 75 factors as 25 times 3 with that perfect square factor of 25, and we can pull out the -1. So the -1 becomes the I. Square root of 25 is 5, so we can rewrite square root of -75 as 5i root 3. Well, as I mentioned before, we defined I in this way so that I is a solution to the equation x squared equals -1. So I squared has to be -1, and this allows us to create some patterns for finding various powers of I. So certainly I to the first is just an I, just like anything to the first power is itself. We just said that if we square I, we get -1. If we want to consider I cubed, well, we can rewrite I cubed using properties of exponents as I squared times I. That's I squared times I to the first. Remember, when you multiply, you add exponents. We just said that I squared is -1, so that simplifies to -I. I to the fourth will be I squared times I squared. I squared is -1, so you get -1 times -1 gives you 1. So we've got the pattern I, -1, -I, 1. Let's continue on for I to the fifth. We can now pull out I to the fourth. I to the fifth is I to the fourth times I. We just said that I to the fourth is 1, so we just get I. I to the sixth we can rewrite as I to the fourth times I squared. We said I to the fourth was 1, so we just get I squared, and we said that I squared is -1. I to the seventh, we can rewrite as I to the fourth times I cubed. Notice again, just to emphasize, this is just properties of exponents, right? 4 plus 1 gives us 5. Remember, when we multiply, we add the exponents. 4 plus 2 equals 6. 4 plus 3 equals 7. Okay? I to the fourth is 1, so we just get I cubed, and we've already established that I cubed is -I. I to the eighth, we can write as I to the fourth times I to the fourth. Both of those are 1, so we get 1. So notice again, we get the pattern I, -1, -I, 1. The same thing happens when we start doing 9, 10, 11, 12. You can pull an I to the eighth off of each of them. You're left with I squared, I cubed, I to the fourth, which again cycles around I, -1, -I, 1. So, in general, notice that we've got multiples of 4 here, right? We've got I to the fourth, I to the eighth. If n is a positive integer and we want to find what I to the nth power is, we're going to divide the n by 4 and get the remainder, and then just do I to that remainder power, like we did in these last two examples, right? For example, 6 divided by 4 has a remainder of 2. 11 divided by 4 has a remainder of 3. So let's do a specific example. If we want to do I to the 27th, 27 divided by 4 gives you a quotient of 6, but it's not the quotient that's important, it's the remainder of 3. So since 27 divided by 4 has a remainder of 3, I to the 27th is the same thing as I cubed, and I cubed is the same thing as -I. If we do 348, 348 is actually divisible by 4, has 0 remainder. So I to the 348th power is the same thing as I to the 0, and anything to the 0 power, besides 0 to the 0 power, but anything to the 0 power is 1. Now that we've established what the imaginary unit is, we can talk about a new set of numbers that are referred to as the complex numbers. Oh, that's a typo. This should be a U here. I didn't type that very well, did I? So the set of complex number we denote with a C, and it's the numbers that are of the form A plus BI, where the A is a real number and the B is a real number. And of course we can't combine these two parts because we have a real number here and an imaginary number here. So we call A the real part of A plus BI, and we call B the imaginary part of A plus BI. All right, so let's talk about some operations that we can do. Well, we can add, subtract, multiply, and divide complex numbers. We just have to be a little bit careful when we multiply and divide, and we'll talk about that here just shortly. We do addition, subtraction, and multiplication, just like we do for polynomials. It's just that whenever we encounter an I squared, we'll change it to a -1. So let's look at some examples. Say we want to add 5 plus 2i and 6 minus 9i. Well, we'll add the real parts, and we'll add the imaginary parts. This is like adding like terms for polynomials. 5 plus 6 gives us 11, and 2 minus 9 gives us 7, so we get a 7i there. Subtraction, we can do the same way. We'll just subtract the terms. So -3 plus 6i minus a -1 plus 2i. We'll get the -3 minus a -1, and then plus 6i minus 2i, which gives us a -2 plus 4i. For multiplication, let's say we wanted to square out 4 minus 2i. Well, squaring means we just multiply the number by itself. If we do FOIL, 4 times 4 is 16, 4 times -2i is -8i, -2i times 4 is -8i, -2i times -2i is a positive 4i squared. We can combine the minus 8i's together to give a minus 16i, and this is what I meant by if we encounter I squared equals -1, we just put it in there. I squared is -1, so instead of 4i squared, we simply have -4. And now 16 minus 4 gives us 12, and we get 12 minus 16i. Division requires just a smidge more work. Before we do division, we'll define what we mean by the complex conjugate. So if we have a number A plus BI, its conjugate is A minus BI. Basically, to get the conjugate, we just flip the sign of the imaginary part. We leave the real part alone, only flip the sign of the imaginary part. The reason why we do the complex conjugate is because we want to end up with a difference of 2 squares. What I mean by that is that if I take a number, a complex number, and multiply it by its complex conjugate, notice that the middle terms here, the minus A minus BI, or excuse me, A times BI, the minus ABI and the plus ABI cancel each other out. We get a difference of 2 squares, A squared and minus BI squared. Well, BI squared is the same thing as B squared times I squared. So we have A squared minus B squared I squared. But remember, I squared is the same thing as -1. That makes this a positive, and we get A squared plus B squared. So notice that when we multiply a complex number by its complex conjugate, we get something that's a real number. We're going to use this to help us do our complex number division. So let's say we want to compute 3 plus 2i divided by 1 minus 5i. Our goal here is to try to get the I out of the denominator, get a real number only in the denominator. So to do that, we're going to multiply top and bottom by 1 plus 5i, the complex conjugate of the denominator. Distribute on top, distribute on bottom. 3 times 1 is 3. 3 times 5i is 15i. 2i times 1 is 2i. 2i times 5i is 10i squared. On bottom, 1 times 1 is 1. 1 times 5i is 5i. Minus 5i times 1 is minus 5i. Minus 5i plus 5i multiplied together gives you negative 25i squared. On top, combine your I terms. 15i plus 2i is 17i. Since I squared is negative 1, we get a minus 10 on the end. In the denominator, the 5i and the minus 5i cancel each other out, and the I squared becomes negative 1, so we get a plus 25. So the denominator is 1 plus 25. Simplifying the numerator, 3 minus 10 gives you negative 7, so you get negative 7 plus 17i over 26. And a lot of times you'll want to write this in what's referred to as standard form. Remember, the form of our complex numbers are a plus bi. So we'll split this up here at the plus sign. We'll have negative 7 over 26 plus 17 over 26i. When we're simplifying square root expressions like we did way back at the beginning, we do have to be careful. We know that, generally speaking, if we do square root of a times b, a square root of a product is the product of the square roots, but in this case, we have to have real numbers to be able to split this up in this fashion. Note that if I do negative 4 times negative 25 under the radical, that particular product is equal to 100, and the square root of 100 is 10. However, if I tried to split it up without taking care of the minus signs first, I would have square root of negative 4 times square root of negative 25. The first radical gives me 2i. The second radical gives me 5i. I would get 10i squared, simplifying that, which gives me a negative 10. So, generally speaking, if you've got two negatives under the square root, you need to simplify it first. Do not try to split it first. You got to simplify under the radical first. The exact same thing is true for division. If we've got 16 over negative 16, well, 16 divided by negative 16 is negative 1, and square root of negative 1 is I. But if I tried to break up my radical first, I would have 4 over 4i. The 4's would cancel. I'd have to multiply top and bottom by the complex conjugate of the denominator, which in this case is negative I. So I have negative I over negative I squared. I squared is negative 1, so we just get 1 in the denominator, and this simplifies to negative I, which is different than the other way. So same idea for division. If you've got a number in the underneath the radical, simplify it first before trying to take care of it as a complex number.